We need to look at springs for the second time, this time in a higher level context. Before, you looked at the energy of springs in mechanics, the potential work done and the force distance graphs. This time we're looking at the mass spring oscillating system, its time period and the energy that it has, and this is in topic 9. Right, you know that in simple harmonic motion the equation is A is equal to minus omega squared x. This is the mass spring system, this is the time period, and the total energy is equal to half m omega squared x naught squared, where x naught is the extension or the displacement. We need to look at what happens if we change the mass or on the time period and the energy. So why does the spring exhibit simple harmonic motion? To look at this, we need to go back to Hooke's law. We know that the force is proportional to the displacement. F is equal to kx, in other words. But you know that F is the unbalanced force, which is ma. We rearrange to divide by m. We find that A is equal to minus k over m times by delta x. Now, this should be familiar. This is exactly the same form as A is equal to minus omega squared x. So k over m is equal to omega squared. The kind of question you could get is, what effect does doubling k have on the time period and the energy? Second question, what effect does doubling the mass have on the time period and the energy? So this is the first equation. What happens if we double k? If we double k, it means that we halve m divided by k, which means that t is divided by the square root of 2. Since frequency is 1 over the time period, it means that the f is multiplied by the square root of 2. But omega is equal to 2 pi f, and we want to find out what omega squared is. So instead of multiplying by the square root of 2, we multiply by the square root of 2 squared. So it's multiplied by 2. So A is equal to minus omega squared x. We know that omega squared is multiplied by 2, so the acceleration is basically multiplied by 2. We double k, you double the acceleration. We also double the energy. So the acceleration is multiplied by 2 and the energy is multiplied by 2. What happens if we double m? Now if we double the mass, it means that the time period is multiplied by the square root of 2. But F is equal to 1 over t. So omega is divided by the square root of 2. But we're interested in omega squared. So it's divided by 2. Omega squared is divided by 2. So let's go back to this formula. There are two things going on here. One is the mass is multiplied by 2. The second one is omega squared is divided by 2. So between them, changing the mass affects m and omega squared, but in opposite ways, so the effects cancel out. So this means that if you double the mass, the total energy is going to be the same. But if you look at the acceleration formula, since omega squared is divided by 2, the acceleration will be half of what it is. And this makes sense. This is in agreement with Newton's second law. If you double the mass, the acceleration will be half.